Hello everyone, this is Miss Lindsay. Today we're going to talk about section 15.6, dealing with compound probability. Go ahead and pause the recording right now. I want you to go ahead and answer those two questions to the best of your ability. We have talked about union and intersection earlier in the year, so go ahead and answer those to the best of your ability at this moment. Okay, so for the first one, we're dealing with the union. The union of those two sets would be the set 2, 0, and the intersection of those same two sets would be 2. So let's talk about the difference between these. Well, union, as you recall, this is an OR problem. Use the U to stand for union. This is when we combine both sets together. You'll often hear me say weld the two sets together. So in other words, combine everything in both sets and put them in one set. Intersection. Here we use the upside down U to stand for intersection. This is where do the sets overlap? Or in other words, what's in common between the two sets? Okay, we use OR as a union problem and as an intersection problem. So if you take a look here, we have the probability that A union B, so the probability that A or B occurs, is equivalent to the probability of A plus the probability of B minus the probability that A intersect B. Okay, so let's take a look at the first type of problem here, and please notice that this is an OR type of problem. This is a union OR type of situation here. What is the probability of drawing an ace or a red card from a deck of cards? So if we use our union from above, we're going to do the probability that we have an ace or a red card is equivalent to the probability of an ace plus the probability of a red card minus the probability that it's both a red card and an ace, so it's a red ace. The probability that it is an ace, there are 4 aces out of 52 in a standard deck of cards. There are 2 suits that are red, so we have a total of 26 out of the deck of 52. And now we have to subtract off the common denominator, because what we've actually done is we've counted 2 red aces twice here. So we need to actually subtract off those 2 aces that are red because we've counted them twice. And if we go ahead and solve that, we would get that to be 7/13. I would like to point out that this has to deal with mutually exclusive cases. This part here where we have the probability that A intersect B. So if we have events that are mutually exclusive, so in other words, the events have no common elements, then we actually would not have to include this last portion. So if we take a look at our example here, what is the probability of drawing an ace or a red card? They do have common elements, hence what we were talking about when we have 2 aces that are also red, we would have to subtract those off. Our next type of problem is with the intersection problems, or in other words, AND problems. So here we have the probability that A intersect B is equivalent to the probability of A times the probability of B. So let's take a look at our first example here. A number cube is rolled and a coin is tossed. Now, before we actually go into this example, let's talk about this event just a little bit. These are actually what you call independent events. So if we take a look at our example here, we have a number cube is rolled and a coin is tossed. Those 2 events are independent because if I roll a number cube, it does not have an effect on the toss of the coin. However, if we are talking about cards, for example, if a card is pulled from a deck of cards and not replaced, the outcome of the second card that is pulled does depend upon the outcome of the first. Therefore, those would be not independent events. Okay, so when we're dealing with our AND problems, we are talking about independent events. Okay, so let's go ahead and go back to our example here. So a number cube is rolled and a coin is tossed. What is the probability that a 4 is rolled and a head is tossed? So according to our problem up here, we have the probability that a 4 and a head is tossed is equivalent to the probability of 4 times the probability of rolling or tossing a head. So the probability of getting a 4 is 1 out of 6 times the probability of tossing heads is 1 over 2. So we get that to be 1 over 12. Let's try a couple more examples here. A die is rolled 3 times. What is the probability of rolling an odd number followed by a divisor of 4 and followed by a multiple of 3? So I'm going to circle that and problem. Therefore, we are going to have an intersection problem. So we will need to multiply the probabilities of the events. So the first one will be the probability of rolling an odd number times the probability of rolling a divisor of 4 times the probability of rolling a multiple of 3. So the probability of rolling an odd number, again, we have a die, so we have the numbers 1 through 6. We have odd numbers 1, 3, and 5, so that would be 3 out of 6, or a half. Probability of a divisor of 4, divisor, what divides into 4, 1, 2, and 4. So again, that would be 3 out of 6, or you could reduce to a half. Times the probability of a multiple of 3, so we have 3 and 6, so that would be 2 times 6. And again, you're welcome to reduce those. That would be a third. If we multiply those and reduce, we get that to be a 12th. Our last example. When rolling a number cube, what is the probability of rolling an even number or a divisor of 10? Again, let me circle the or. So now we know we are doing a union problem. Okay, so again, when rolling a number cube, what is the probability of rolling an even number or a divisor of 10? So we'll have the probability of rolling an even number plus the probability of rolling a divisor of 10 minus the probability that it's both an even number and a divisor of 10. So the probability that's an even number, so we got 2, 4, and 6, which will give us 3 over 6. Probably a divisor of 10, so there we have 1, 2, and 5. So again, 3 out of the 6. Minus the probability that it's both. Well, our even numbers were 2, 4, and 6. Our divisors were 1, 2, and 5. So we counted 2 twice. So we have to subtract 1 over 6, which gives us 5/6. And this concludes section 15.6 notes.